I guess I just have to. Recording is in progress. Okay, so you didn't hear me describing this whole EUV lithography business then?
We did hear you, we just couldn't see what you were talking about.
I see. Okay, well, this is the system. It's about the size of a school bus. It's based on the existence of these polysilicon coatings shown at the bottom here. So molybdenum, silica, and alternate layers. And with that, you can get a normal incidence or near normal incidence reflectivity of about 70%, as we saw on a slide previously. And it operates with a laser at a CO2 laser at 10.6 microns, that's the wavelength, being focused on little tin spheres, typically 27 microns in diameter. So a 10.6 micron laser focused onto a 30 micron or less sphere. These high power lasers are not the best to focus, so much of the radiation from the laser would miss the 30 micron or 27 micron tin sphere, and so it's useful and critical, it turns out, to use a pre-pulse. And with that, you create a plasma. So I'm going to skip to the next slide, I think. This one. So what happens is a laser pulse, CO2 laser pulse, comes and hits each of these spheres. So the spheres are coming down. They're all tin, as indicated here, droplets. And laser pulses are coming to hit every single one of them as they go by. And each laser pulse hits a sphere and is absorbed and heats up. And it gets hot enough that it emits EUV radiation. And the idea is to optimize that emission to match the polysilicon coatings. And the wavelength that does that well is the 13.5 nanometers. So these droplets are coming along. These are some of the plasma parameters. We'll come back to this, so it's not quite so critical. Okay. One of the issues is you've got 12 different optics. So if the reflectivity is 0.7, which was a miracle, but there's 12 of them, you wind up getting much of the power, it turns out, doesn't get all the way through. So you're losing a few orders of magnitude. Okay. So it's a step and scan system. So for instance, you print this pattern as shown here with a thin curved slit. So you're imaging, there's an imaging optic here. Here's the CO2 laser. Here's the droplet coming by. It gets heated, it emits EUV, which is half of it's lost, but half of it is caught by this collection optic and reflected into a system which illuminates the mask. The mask is what has the pattern, the electronic pattern. So these optics are all used to just image, to put this spherical illumination into a slit pattern, because that's what's needed for an optimum illumination in which aberrations are corrected only over this narrow slit, not over the whole pattern. So this is the so-called mask. It has the electronic pattern, and that pattern is imaged by these optics onto the wafer. The wafer is a resist-covered material that absorbs this imaged pattern here and prints it, or records it, I should say. So this is only using a slit, so the mask is moving along in front of this slit of illumination. The optics are stationary, but the mask, the wafer is moving in the opposite direction. Whoops. Opposite direction. So it's called a step and scan system. You step to the next area and you scan it and record it in the wafer. Okay. So this is, for instance, it is a 300 millimeter wafer. And if you can see me, here is a 300 millimeter wafer. So 30 centimeters. Okay, maybe I should get back further. Okay. And this is pattern. So the one side is just a reflective silicon. It's a beautiful mirror. Okay. All wavelengths. It's like an aluminum mirror, but it's silicon. Interestingly enough, silicon for visible light is a perfect reflector, okay? But SiO2 would be a perfectly transmissive window. So, okay, so this is the step and scan wafer. This is the coating we've seen before, the polysilicon coating, which is going to have a normal incidence reflectivity, which is quite high, around 70%. It's called, it's polysilicon, but between each layer, there's a little B4C. It prevents diffusion of, when you're coating it, prevents the moly from going into the silicon, and then when you're coating the silicon, prevents it from going into the moly as you do layer after layer. Again, we'll talk about that when we get to optics. And this is the droplet system, okay? And this is just some things, if you want to read them more there, I reposted this chapter because I added a few slides at the end, but basically in 2017, well, in 2017, after more than a decade of nothing happening good on EUV, it just didn't seem like it would make it into high volume. The people at TSMC, in particular a guy named Tony Yen, worked with Cymer, who was making the source, and they introduced a pre-pulse. It was a pre-pulse that should have been added more than a decade earlier, but it wasn't. And it played a critical role, and their EUV power went from 9 watts to 90 watts, a factor of 10. And since then, it's gone to 250, and I imagine now it must be up around 500. And with that, Intel announced it was making $1 billion purchase of all the tools that the company ASML, they're the ones who made that small bus, the stepper. And inside of that, by the way, Zeiss made the optics, and Cymer here in San Diego made the little droplets and the CO2 laser. It all comes together in a tool that ASML manufactures in the Netherlands. Anyway, Intel said they would buy $1 billion worth, if you can imagine. Also buying was the Taiwan company TSMC and Samsung in South Korea, and they both went into high volume manufacturing starting in 2018, really I guess 2019. And now, for instance, your latest iPhones and many other things, and also the Samsung phones, cell phones, are all made with this new technology. And whereas Moore's law seemed like it was over, it's not over anymore. Now it's moving, and it's going to have quite a few generations. And for instance, you see here about making the iPhone 11 and 11 Pro and stuff like that. So different announcements are out, and a technology which had a long birth is now off and flying. So, and then I wanted to bring to your attention, this will help you with the homeworks, but it'll also help you with the readings. There's no big errors in the book, but there are annoying misprints. And somehow or other, I didn't catch them, although I thought I proofread it so carefully. But there are places. So there's an errata, which I posted, I think, last week on the B-Course thing. And I urge you to get it and correct your text. It won't make such a big difference in the first homework, but after that, as you're reading, it'll just be annoying. There'll be things which maybe you'll recognize as being wrong, but they're not. Anyway, there is an errata. It's several pages. I urge you to get a hold of it and correct whatever you're reading. Also posted were some formulas, and you might as well download those. I don't know if you can download them to your phone or what for convenience. I've laid it out here in one way, but it comes in just a sequential thing that covers all the chapters. But these are the kind of formulas. So some formulas you've seen from chapter 1, some things that we're going to use in the homework. So for instance, one of these gets used in the homeworks that will be assigned on Friday for the following week. And then this is from chapter 3 about refractive index, and there are others. All the chapters are represented. So
I have a question.
Yeah, great.
I think Angel has his hand up.
Yeah, go ahead, Leona. Who was
no,
asking the question?
I didn't. There's a hand up. I didn't know if it was still up from before or not.
Yeah, I think it is. I checked a little while ago. I remounted chapter 1 slides because I added those few things. And I'm also mounted the ones for today for chapter 2. So those slides are all on B course. And I remounted a new homework version for chapter 2 because I found some wording in the old version I didn't like. I thought was unnecessarily confusing. So I mounted all of those things. So over this thing. Can you go back with, suppose, I'll just ask you to advance this slide. So let's start there. Okay, so we need to do some electromagnetics here using Maxwell's equations. So these are the defining equations, governing equations for the electric and magnetic field in the presence of some current, J. This is written as if it was in vacuum with a bunch of charges and currents. And that there are various ways to write Maxwell's equations with some refractive index or other things, but doing it in vacuum is a good way is a convenient way to do it. It works very well for plasmas and it's going to work for us. And so what we need to do, we're going to need some relationships here between, for instance, when there's no current, when we're just in vacuum without any charges, we want to have a relationship between the electric and magnetic field, and we want to find out about the flow of energy, which is E cross H. It's a vector flow of energy, power per unit area. The magnitude is the intensity, which is an extremely important parameter. So at a fundamental level, you want to know the electric field, let's say, but we don't measure electric fields generally in the laboratory. We measure intensity, which is E cross H. So we're going to have to find some relationships between E and H and I. And offhand, these equations are complicated. They've got curl operators in partial respect to time and divergence operators, and not so easy to do it. But there is a cute little trick where you represent each of these fields in a Fourier as Fourier components. I'll show you what I mean in a moment. And in each of these equations, everything will have these same components except for amplitudes. And we'll find some cute little trick where we can relate E and H and all of the other things. Another thing that we need is a wave equation. A wave equation, so all of these things that we're going to do are going to be the same for any electromagnetic. So it could be microwaves, visible, ultraviolet, whatever, but it also works for X-rays, and including when we calculate obtain a formula for refractive index. It would be a refractive index that would work, it would be a formula that works as well in the infrared, the visible, or whatever. So we'll need to obtain that wave equation, and I'll show you how to do it in a few steps, okay? But it's a slide coming. But anyway, if you combine these equations, you'll get a wave equation. This is the form of a wave equation. There's an operator like this operating on the electric field, and it is driven by a current. So in vacuum, this would be 0, and it would just be the propagation of the wave as described by this. But I'll show you a few aspects of that, which are quite convenient. So I'll show you how to, there'll be a slide just of how you go from Maxwell's equations to the wave equation. So Leona, can you give me the next slide? Oh yeah, okay, so in chapter 2, we're going to talk about radiation. We'll get parameters, relationships that we need, so some electromagnetics, but we'll also look at scattering cross sections. What happens when an electromagnetic wave of any wavelength comes upon an object and it causes the electrons in that object, could be a single electron or an atom with many electrons, bound electrons, but the incoming electromagnetic field has an electric field that's oscillating, and when it oscillates, let's say in and out of the board, it makes the electrons, all of the electrons in the atom, oscillate up and down. Some move more freely than others. It depends on where absorption edges and frequencies are, but anyway, they all oscillate up and down and they radiate. If there's only one electron oscillating up and down, it gives off dipole radiation. It looks like spheres just propagating out. If there are many electrons, depending on the scale, the wavelength compared to the diameter of the atom, there could be interference effects between those. They'd all be oscillating at the same frequency, but they could have different phases. So for instance, if the wavelength is a half angstrom, it's smaller than the atom, and so different electrons are going to see a different phase. So we'll get into these factors in this chapter, chapter 2, okay? In the next chapter, we'll look at what happens when you have a lot of atoms, you have a thin film of material, and what happens then. So it'll be just a continuation of what we learned in chapter 2, but we'll see that there is a refractive index written in the following manner. Okay, next slide, please. This is just saying more of the same, what kind of things we're going to learn in this chapter and what we're going to learn about in chapter 3. Next one, next slide. This is just some of the formulas. That's okay. That slide was just some of the formulas that we will be picking up in chapter 2. Mm-hmm. Yeah, chapter 2. Yeah, this is from an older edition of the book, but it has a good formulas in it, okay? Convenient. It's showing that when you have an electron oscillating in an electromagnetic field, again, it doesn't matter if it's microwaves or visible or whatever, the electron is oscillating up and down. It radiates out a donut pattern shown here. It's called a sine squared pattern, okay? And the power radiated per unit power per unit solid angle depends on that sine squared angle, where the angle is measured from the vertical, from the acceleration direction. And this is the formula, and we're going to find that formula, and we're going to use it. And it's a common formula that people derive in both physics and electrical engineering, and we're going to use it considerably, okay? And these are just some of the formulas for the cross sections. So next slide. Yeah, so we'll talk about what is scattering. So basically scattering is the redirection of radiation. It was coming in one direction, and it's going out in many directions, okay? Whether it goes around uniformly in angle or not uniformly depends on the location of the various charges in the atom or the structure compared with the wavelength. But for instance, we will define, this is the normal way to define a scattering cross-sections, whether you're looking at electrons, ions, or X-rays. It's defined as on average, the power scattered to all directions divided by the intensity, basically. This is the pointing vector, E cross H. It represents, it's a vector, has vector property, a direction, but it's power per unit area. And I wish I had put in the text more places that this was the intensity. So it's total power radiated divided by power per unit area. So you see it's got units of area. Power divided by power per unit area, which is what intensity is, okay? It could be isotropic or not. It could have a strong energy dependence or not. So we'll find out when we look at a single electron, just a single electron oscillating up and down, we're going to get this very simple Thomson result that it's a constant. It actually is the same for infrared and X-rays. That cross-section is, okay? But then we're going to look at a bound electron, a single bound electron. You can put H bars on these, so these are all in energy units if you want. But basically, it's a matter of, for this bound electron, where is it compared to the resonant frequency between a transition, okay? And if it's a little bit below, then this is smaller, this is going to have a negative sign on it, but it gets squared. But when we come back to it in the refractive index, the same thing is going to appear, and it matters a lot. And we'll look at some examples of visible light where omega is less than omega s, and you get some really interesting effects. So this is for a bound electron. If you have a multi-electron atom, you have this effect, but you have to do a summation over all the possible resonances. So quantum mechanically, this would be starting from all of the possible stationary states into all of the available states. You'd have to sum over all of them. We'll do a semi-classical version of it, but in the end, it'll look exactly like the quantum mechanical one. And the way you find out what it really is you go to the lab and you measure it. So next slide. Yeah, the last slide, for the multi-electron atom, you wound up with a lot of electrons. You wind up going to the lab and you measure what's called the atomic scattering factor, shown at the top here. So this is for silicon, and there's a real part and a lossy part of that atomic scattering factor. And again, this appears not only in the scattering cross sections, but in the refractive index. And silicon is quite special here. This is the L edge of silicon is at 99.5 EV roughly, or 99.8 EV it says here. And so just around that point, silicon, this is telling you that it's scattering like it has how many electrons? This is an equivalent of electron units. So at a very high frequency, well into the X-ray region, the binding is irrelevant. It's such a high frequency. And in that case, the real part of the atomic scattering factor levels off at 14. It's acting like there are 14 independent electrons, no binding effects whatsoever. And at those same very high frequencies, absorption, which is represented by this, is going to zero very quickly. So we'll be talking about these atomic scattering factors at length, and you'll probably be using them in your homeworks. And by the way, this website, which I've told you about before, you use that whenever you can to solve a homework problem, okay? And in fact, we're going to assign homework problems tomorrow, and I just changed that. So I think there's 4 problems, and you want to use the formulas. I told you at the end of the last, at the end of the chapter 1 slide to go to the B courses and look at the corrections, the errata, but also there's a list of formulas there. Get those formulas and use them, make them convenient for you, because for instance, you'll need them in this you'll need one of them in this homework problem. It's going to come up again in a moment, but you need it. Let's see.
Sir?
Yeah, please.
I've got a question. Unless you're going to cover it later on, but could you just explain quickly what you meant by binding effect?
What did I mean about binding? Is that what you said? Just repeat it for me.
Yeah, can you just explain what you meant by binding effect?
Oh, binding. Yes, I'm sorry. So we had the free electron that was oscillating. It was all by itself. But then suppose we have like a hydrogen atom. It's still also got only 1 electron, but that electron has certain resonances, right? For instance, if you came in with a frequency that was just equal to the frequency, or if you want photon energy, between n equals 2 and n equals 1, you'd have a resonance there. You'd have an electric field that's driving the electron up and down, and it's between 2 perfectly defined states. So the resonance comes in there. It's classically, the example often given is you're pushing a kid on a swing. If you push at a certain frequency, the kid swings nicely. If you do it at the wrong time, you don't have if you do it too frequently or too slowly, it doesn't go as well. But if you do it just at the right frequency, you have to be careful you don't send the kid around the swing. So for every electron in an atom, there are transition states that it can go between. And if you come in with an X-ray or an ultraviolet frequency that matches one of those resonances, it has a big effect on the scattering amplitudes, and the cross sections will go up, can go up enormously, many thousands. So that's what I meant by binding. Is there a binding energy or a resonance associated with the possible oscillations of this electron? I'll show you an equation in a moment.
Great, thank you.
Is that okay?
Yes, sir.
Okay. So, okay, this is a slide. It's a standalone slide. We start with Maxwell's equations, one of them, okay? The curl of E equals minus the partial of B with respect to T. So E is the electric field, B is the magnetic field. And if you take the curl of that and use a vector identity, which is in one of the appendices, there's a few other steps you have to take, but basically you'll get this, which is the wave equation. Here's the operator. This is the wave operator acting on the electric field. You could have done it in terms of the magnetic field, but we work with electric fields more. And there were some extra terms left over from Maxwell's equations on the right side. One was the current density J, and one was gradients in the density. So in vacuum, there are no currents and there are no charges. So this is 0. And this is our wave equation in free space, okay? And by the way, there were various factors that were mixed in there. There was a mu, we replaced B by mu H, and a D by epsilon E. And when you put all of those things in, when you're combining them, the details it says are on page 28, you'll find that they combine into what we recognize as the phase velocity of the wave. This is a wave equation, and whatever that is there is the phase velocity. And in the, just the terms that collect to that, this is it. So square root of epsilon 0 over square root of epsilon 0 mu 0, okay? Okay, so that would be our wave equation. The J is the charge. So if it's an electron, it's minus E. If we had plasmas, we might have a plus E Z or something like that, charge on the ion. But for us, for the electrons, it'll be minus E. N is the density of electrons, perhaps. Later on, it might be the density of atoms. And V is the oscillating velocity in this electric field. So there's a wave coming by. Here's our wave equation. There's a wave coming by, electric field. It's oscillating with some frequency, and it is driving a velocity modulation, okay? So that's basically a case of F equals ma, and we'll see the equation in just a moment. We're interested in transverse waves. Oh, go back again. I didn't mean to change it yet. We're dealing with X-rays. These are electromagnetic waves. We're going to be in vacuum, and so we're dealing with plain electromagnetic wave, transverse electromagnetic waves, right? So this is not an acoustical wave, and if it's not acoustical, you would find that this term, which involves the gradient of the charge, and the longitudinal part of this current, the current has a transverse component and a longitudinal component in the coordinates of an propagating electric field. This cancels out with the longitudinal, and all you're left with is this thing at the bottom. You could have just say, okay, I'm just going to take transverse components. This doesn't have a transverse, this has a transverse component. Transverse to its propagation director. I get the transverse component here, and there is no transverse component here. You get this equation. So this is what we'll be dealing with. This is our wave equation, and this is what J is, and we'll take the transverse component of that, would give us a transverse component of the velocity. So next slide, please. Yeah, so we have a wave equation now, but we also need a relationship, something that lets us know about power flow. And the thing in the right here is telling us that we're going to identify in this slide that there's a vector called the Poynting vector, which is E cross H, so vector cross vector, and it is the power per unit area, and it has a directionality to it, so it's a vector quantity, okay? What's extremely important is that the magnitude of that Poynting vector is the intensity of the wave in watts per centimeter squared. So this is something you want to know if you're focusing radiation down, to what intensity, okay? And okay, so, and in calculating, for instance, the cross sections, the scattering cross sections, we're going to need to know what is this incoming intensity. We're going to calculate the total power radiated, but we have to divide by the intensity or the magnitude of the Poynting vector. So this is just telling you, I'm not expecting you to follow this right now. If you're interested, you can follow it up in chapter 2 and see where this all comes from. But it's telling you what to do. What is the formula for how to get the Poynting vector? And if you follow these equations down, you'll find that you get this differential equation. It says that the divergence of E cross H is the partial with respect to time for what's recognized as the magnetic energy and the electrical energy stored in the electric field, and a power term in E dot J. And so it's through this formula that one recognizes what is power flow. This is the increase or decrease in magnetic field energy, electric field energy, and maybe some power was either put into the system or taken out of the system. But at any rate, it's through that you recognize that this E cross H is the power flow, vector power flow. And you can integrate this using Gauss's divergence theorem, and you get this relationship. And the only reason we have to look at this, I could have just told you, listen, the power flow is E cross H, but just in case you're interested, this is where it comes from. And this is just pure electromagnetics that people have been doing for microwaves and visible and infrared for a long time. And you see here where they recognize these things as stored energy and energy put into the system or dissipated. So, excuse me, what is coming next? What is it? Yeah. Okay, yeah, so we need some relationships here between E and H and S. For instance, we're going to wind up using a relationship between the intensity and the electric field and back and forth. It's actually a square. The intensity is proportional to the electric field squared. But we need some relationships amongst all of these things. And so between E and H and S, all vectors. And now we're going to, I'm going to show you a trick, which you may already be aware of, and maybe you're not. But if you're dealing with Maxwell's equations or the fluid plasma equations, these are also quite useful. So, excuse me, just a second. So I want to replace B by mu H. That's mu zero for vacuum H. So I have this equation now for the electric relationship between the electric and magnetic field, but it's not quite so simple because one side's got a curl and the other one's got a time dependent, and you can't get, it's not obvious what the relationship is between the two of them. And so here's where we play a trick, and one of your homework problems is to reproduce this in one particular form. We're going to represent the electric field in space and time as a summation, actually an integral, of the electric field coefficients. They're labeled E, K, and omega, and exponential e to the minus I omega t minus k dot r. So omega is the oscillating frequency. K is the vector wave direction. So K, the magnitude of K is 2 pi over lambda, but it's a vector. So that's your K, okay? So for our X-rays, this will be the frequency. Put an H bar on the omega and you'll have photon energy. The K is 2 pi over lambda, where lambda is, let's say, the X-ray or EUV wavelength, okay? So we're going to do that for E, represent the electric field in terms of E, K, omega. They're like coefficients, okay? And H, we're going to represent in terms of its coefficients. Other than that, they both have the same Fourier style of representation in terms of waves of this nature. This would be the propagation of a wave, okay? So what this does is it takes these vector relationships and it algebrizes them. It makes them algebraic operators instead, and we can divide and multiply and things like that. So for instance, this equation up here, you can show, and this is where you have to go look in the book, that the curl operator, which I presume you're all aware of, can be represented by I times K, vector K. And the partial with respect to time, if you took the partial with respect to time of H here, none of these things depend on time except this one. So when you take a partial with respect to time, this minus I omega comes out, and you can take it through the integral, okay? Here, if you took a curl here, it would just be operating on the k dot r. It's a little messy, but it's in the book, and it's not all that hard to follow. But this relationship then comes down to looking like this. Okay, the vector relationship is now been algebraized. It's still vector quantities, but for instance, the time derivative is just it was a minus I omega. So now you can write what is your relationship. What is H? How does H depend on E? Looks like this. Okay, well, we wanted to know if you then take inverse operators, you take the inverse of these operators, again explained in the text, you replace this by the inverse of this operator, and you find that the relationship is the following, that H and E are related by just a cross product with a unit vector, okay? And similarly, you'll find that the Poynting vector, E cross H, is just this. It depends on the magnitude of the electric field squared going in a vector direction, okay? And the average, if you do a time average over one cycle, a factor of a half comes out in front. It's just from, there's an electric field, let's say it has a sine or a cosine, but at any rate, when you square it, an average over one cycle, you get a factor of a half. So here we have now relationships between E and H and between the Poynting vector or intensity and the electric field. And this is what they look like. And again, this is a reminder, this magnitude of S is the intensity, okay?
Professor?
Yeah. Mm-hmm.
Just a clarification question. When we're looking at the K vectors in these, are these unit vectors? Or are they like full vectors?
Thank you for asking that. With a subscript 0, it's a unit vector. But up here in other places, it's not. This is a K vector. It's got 3 components depending on which is the propagation direction of the wave. So it could be just KZ in a one direction, but it could arbitrarily, could have any direction. So remember the dipole radiation of radiation, it's going all over the place. So K would have multiple components. But here is the unit, this is a unit vector, right? Great, thank you for pointing that out. So I think we're ready to go to the next slide. Yeah, so there was a relationship in that previous slide between the intensity and the electric field, yeah, here. So remember that if we took the magnitude of this, that would be, which one do I, that would be intensity, and this would be electric field. The vector part, we take just the magnitude, the unit vector goes away, and this just becomes the scalar electric field. And so between this, you'd have a relationship here between the intensity and the electric field, and these are parameters you got to deal with. And if you go to the next slide, it's one of these relationships. One is, here's the intensity in terms of the electric field squared. Subscript 0 here means that it's the amplitude. So it's E0 sine omega t, or E0 cosine omega t, okay? So it's saying that the intensity is this number in front times the electric field in volts per centimeter. Remember, the way this works is if you see brackets, you just put in the number. So if it was 10 to the 9th volts per centimeter squared, you just replace this by the 10 to the 9th, okay? Cancels this. And the unit that's left over for the intensity is watts per centimeter squared. So this is the most common form in using lasers. Lasers are intense radiation. You normally write intensities in terms of watts per centimeter squared. So for instance, the high harmonic people will operate at intensities that the Ti-sapphire laser focused to 10 to the 14th watts per centimeter squared. You could then ask, okay, what is the electric field? If this is 10 to the 14th watts per centimeter squared is the intensity, just replace this bracket by 10 to the 14th, take a square root, these cancel out, and you'll have the electric field in volts per angstrom or volts per nanometer if you choose. So one of these formulas you wind up using in the homework for chapter 2. And they're also, they're sort of everywhere. They're in the formulas that I gave you, that that I posted in B courses, and they're also appear in the errata just because I thought it was convenient. Okay, next slide, please. Okay, now we'd like to know if there's a current J, what is the resulting electric field? So we're going to use the same trick again with the Fourier components and the time derivatives and the gradient operators. But basically we're going to want to know, for example, if we want to know the scattering cross-section for a free electron, we're going to have an equation of motion, basically an F equals ma in terms of the electric field and the mass of the electron, and it's going to oscillate up and down and produce a current. And we'd like to know what electric field does that produce, and what about E cross H, and what about the total power radiated? So we need to start with these things. So to get, so now we're trying to get a relationship between the fields, the radiated fields, and some current density J, which we'll write initially for a free electron laser and a free electron, and then later for some bound electrons, meaning electrons that are on an atom that have binding energies. So here's our wave equation, and we are again going to represent the electric field in terms of Fourier coefficients, a wave of this form. It's just a complete set of waves, okay? And we'll have to integrate it over all frequencies and all wavelengths. And by the way, this is not a vector, it's just a shorthand way of writing in 3 coordinates. So dkx, dky, dkz, okay? And if we do that for the electric field and for the current and everything else, and well, let's start here. We have the time derivative twice. So a time derivative on the electric field is going to pull out a minus I omega. That's going to be able to come out of the integrand because there's nothing, this is just an interval in frequency space. It's not a frequency dependent. So this comes out, and if it's a second derivative, then you're going to get a minus I omega squared. So this term is going to give you an omega squared. And this term is going to have the minus c squared, but this vector operator in the direction of propagation is just going to become I times the vector k. Again, this is not k0. This is the wave vector, okay? And again, these things, this got squared. So this is what you have now. This is your wave equation in terms of the coefficients or the amplitudes in k and omega space. So for a certain frequency and wave number, it would be a propagating wave, okay? This is the operator, and this is on the other side of the equation, this is what the transverse component of the current looks like. So let's look at the next slide. There's some interesting things here. So this is just rewriting that same equation at the top, but some things that this is just simple mathematics, ordinary differential equations really. Suppose you were in vacuum and there was no current, so this was 0. Then you'd say, okay, how can I have a wave propagating in vacuum with a finite electric field if this is 0? Well, this can be finite if this is 0. The operator is 0. So you can have a finite field propagating with no driver, no current, in vacuum whenever this is 0. So omega squared minus k squared c squared is 0. That tells you the natural modes of the system. So it has solutions, omega equals plus or minus kc. And if you write omega is 2 pi f and k is 2 pi over lambda and recombine them, you'll have f lambda equals c. So this is the propagation of a wave in vacuum. We haven't said anything about X-rays yet. Okay, and what else to say about, oh yeah, and there are 2 solutions. It's a second order. So there's a wave going to the right and a wave going to the left. Or if you're in radial coordinates, there's a wave going radially out and a wave coming radially in. So it's just a second order, okay? We can then we can now go back, just having made that observation, interesting observation. Let's go back to this equation and solve for ek omega. What do the coefficients look like? It's like this. So this is where we've now we can see the power of having algebraized everything. We're not dealing with all these, all the curl operators and the time operators. And we're saying that the amplitude depends on this. We can go back, we can put this back into the Fourier equation and solve for E of RT, which is what we really want to know. And we'll have this here within the integral, in the integrand, and the opposite was, these are the opposite things. Now we're integrating over d omega dk. I have a 2 pi to the 4th. You know, when you do Fourier transforms, you can do square root of 2 pi and square root of 2 pi, or you can leave them all on one side and make it just 1 and 2 pi. And because we have four dimensions, 3 in space and 1 in frequency, we get a 2 pi to the 4th. But now we have solved the electric field. This tells us what is the electric field driven by some current oscillating up and down. This would be the formula. This is a Green's function. Okay, this is the Green's function. You're solving for the electric field in terms of any arbitrary current, and you have to deal with this. So this looks like, oh my goodness, when we do integrations over omega and k, there's going to be a singularity here. How are we going to deal with that? So think of Mr. Cauchy, the Cauchy-Riemann equations. That's what we're going to solve this for a single electron oscillating in an electric field. So that brings us to the next slide. Okay, so we're going to have our current for this oscillating electron. This is the way it's normally written. We're going to say, actually, our point electron is so small, we can represent it by a delta function. Okay, there's still a velocity here and a minus e, but the charge distribution of our electron is so small we can use a delta function, where this is written in this form. This vector form is just a shorthand that the delta function of this vector r is really just a product of three delta functions. And the delta function is, you know, has the property, it's 0 except when x is 0, but when x is 0, it's infinity, okay? And it's normalized this way. So these are probably things you've learned in your math classes, vector math classes and the like, several years ago, and this is a reminder, but it is in the book, you can read it. And now we're going to use that, okay? And in fact, just like we did everything else, the jk omega that we needed to put in that integral, before we could use the Green's function, we had to figure out what is this jk omega? Well, this is the way we would write it, okay? And the j, so this is the inverse Fourier transform, or this is the Fourier transform. And now for the j, we put minus e delta function of r, v of t. Well, the delta function of r and the integral over dr, boy, that's going to be easy, right? That's just a 1, okay? And this, this will be 0. And this is what's left over. And this we recognize as, just the Fourier transform of v of t. So if we knew what v was, what is the oscillating velocity of electron in an electromagnetic field? It's going to be charge E, electric field E divided by the mass of the electron. It just comes from F equals ma. We're going to get this velocity, and we're going to be able to go and calculate. We will then have a relationship for the current amplitudes, and we're going to put it back in that Green's function. So I think I'll just show you one more slide today, I'm thinking. Yeah. So this is what we were talking about before. We found a relationship that the electric field depended on this. It was really an inverse Fourier transform, but it looks like a Green's function. It is a Green's function. And now we have a current here that we're still going, we could do it right now, but we're going to write it this way. We're going to leave it this way for now, and we'll calculate later what it is for a free electron or a bound electron. So we'll put this in here, and now we have to do an integration with these poles, right? There's 2 poles here, one at plus Kc and one at omega equals plus or minus Kc. So we have to do an integration in the complex plane. So if you're not up to or not interested in following the integration in the complex plane, it's okay with me. but then you just have to accept it. But it's easy enough to follow. But again, you can just follow it. If you make these substitutions and you assume that there's a really small imaginary part, it just moves the two poles slightly off axis, and then you close in the upper half plane, and you wind up doing these integrations, and you find that the electric field for an oscillating charge, an electron, the electric field is equal to the transverse acceleration at a retarded time. There's a T minus RC comes into this. So in other words, if you were right at the electron, R would be 0, but if the electron is oscillating far away, some distance R, then it takes a little time to get to you. That's what this means. The oscillating charge in what's called retarded time, okay? And right, and it has, the electric field has a 1 over R dependence, okay? So maybe let's take a look at one more slide. Get this out of our way. This doesn't have the F equals ma. If you take that electric field and you form the E cross H that we were talking about before for the pointing vector, if that's the electric field, what does the radiated field look like? And follow this algebra down, and you'll find that you'll find all of these things here. I have to look here. Right. So because of our relationship here, the intensity or the vector, pointing vector, depends on electric field squared, and we had the electric field here. We're going to, we see that the radiated power, which is a vector, goes in different directions. So K0 is a unit vector, but it can be propagating in the wave direction, which could be aligned at right angles with the acceleration direction or not. So these are unit vectors in a coordinate system for the wave, and the wave is shown here as propagating at an angle capital theta from the acceleration. And if you put those things in, you'll find that this is the power, this is the vector power radiated. It depends on the acceleration squared, which you probably already knew, and the sine squared, it depends on the angle measured from here. So if you're radiating just along the acceleration direction, there's no power radiated. But at right angles, it's the maximum. That's what the sine squared. And the power radiated goes down as 1 over R squared. Electric field went 1 over R. This goes 1 over R squared. You can replace some of these things. You can replace the vector power flow in terms of a power per unit area in some direction. And you can replace the area by an R squared times d omega. And that will allow you to put this formula in terms of power per unit area, okay? And we're going to use this. The next slide will be the F equals ma, and we'll replace this A, and we'll get the power per unit solid angle radiated by an accelerating charge. So I keep saying we're done, but let's look at one more slide, if you don't mind. It still doesn't show it. Okay, we'll come back to this next time. But basically we'll write, here it's showing that you can integrate over all solid angles and you'll get the total power radiated in terms of accelerated squared. But this, for writing this acceleration, we'll do a simple Newton's law, F equals ma. So let's break there, and I'll come back to this slide next time. You should take a look at this in the chapter, just that you sort of get the flow of ideas, and you don't have to follow, you don't want to get lost in all the math, but you do want to follow why we're obtaining those relationships and what are the relationships. Okay, so let's, does anyone want to make a comment? I would say this is one of the toughest chapters that you've got in the whole book, but this is electromagnetics. This is what you do. And by the way, this power radiated per unit solid angle, the dipole pattern, that is the radiation pattern of a single oscillating electron, which you would learn about in the physics department in 110B. I presume, 110A or 110B in the physics department, that dipole radiation power, the donut pattern, that would be shown there for a single electron. Whereas you take a class, same class in electromagnetics, in an electrical engineering class, and it might be an FM antenna or an AM antenna where it's not an electron going up and down, but it's a current of electrons going up and down, and you would get that same dipole formula. So the antenna is pointing up and the radiated power is maximum across the horizontal plane. Okay, I guess if there's no questions, we're ready to go, and hopefully next time I'll have figured out what I was doing wrong here. Okay. No questions? We'll go. Okay, bye-bye.